I lost my mood ring. I just don't know how I feel about it. So a lot of what we have done so far using derivatives to analyze an original function has dealt with f prime, but today we are going one step further and looking at what f double prime will tell us. So it's f double prime's time to shine. And really what we get out of f double prime is concavity. So of course if we're looking at particle motion, it tells us acceleration, and that's important for particle motion. But when we are looking at a function itself and trying to get more information about f of x, then if I'm going to a second derivative, it's going to tell me about concavity. So in its simplest terms, if I'm saying that something is concave upward, I'm just saying that it looks like this. So like a positive parabola is concave up. If it's concave down, it's frowning. If it's concave up, it's smiling. But calculus-wise, we've got a couple of different ways to say that. We can say that a graph is concave upward if f prime is increasing, because that would mean that f double prime, the slope of f prime, is positive. So we'll look at how that works. And it's concave down if f prime is decreasing, which would mean f double prime is negative. Another way that we can look at this, we're like, I'm still not sure if I can tell by looking at it if it's concave up or concave down. If we're concave upward, we're saying that all of the tangent lines lie below the function. So look at our function right here for f of x. We have this piece right here is concave upward. So if I was drawing my tangent lines and it was just going along here, they would all be below the function, where if I'm concave downward, all of my tangent lines are going to be above our function. So that's another way. Now somewhere in there it changes, and that is called a point of inflection. So below, we've got this place to say when our concavity changes. So our point of inflection is the point where concavity changes. So for f of x, we don't know, I don't have any numbers here, but it's somewhere around there where I can tell, okay, it's concave down, and then all of a sudden my tangent lines are now below it, and now I'm concave up. It occurs when, oh wait, we'll get to that eventually, that's too much. Okay, so before we get to all of this, which we've answered several of these things before, we're adding in a few new things. Let's go ahead and sketch over here so we can connect as we go the graphs of f prime and f double prime. So remembering that if I'm graphing f prime, I'm saying this is the slope of f. So the easiest way to start this is to pick out any zero slopes for f of x. So right here I've got a max, so this is going to have a slope of 0. My horizontal tangent there would be 0, and you can draw that if you need to. I've got a horizontal tangent right here, so I'll have a 0 on f prime. And then I'll have to use my slopes to go from there. So I've got a positive slope to begin with, so that just means that f prime is going to start above. So I'm going to go ahead and put this point above, and I'll connect here in a minute. After I get to that max, now I've got a slope that is negative. So I'm going to be below the x-axis for this whole point right here. So maybe I'll give myself a little big point there. And then I'm going to be increasing again, so I'll be above the x-axis until my endpoint. Now I don't know what exact values these are, this is just estimating, but I will end up with a function that looks something like this. Not too shabby. Kind of parabolic. My original was kind of cubic, so it makes sense. If I go a step further and I find f double prime, now I'm finding the slopes of f prime. So I just had the one place that has a horizontal tangent right there, and then I have a negative slope to the left and a positive slope to the right, so it will end up looking something like this. So I know it goes from negative to positive, that's the place where it's 0. Okay. So what I want you to notice, so we can add in the occurs when, that the 0 on f double prime is the exact same place where I had the point of inflection on f of x. And that's not a surprise. That happens every single time. So my point of inflection actually ends up being a 0 on f double prime of x, or I can say that that point of inflection occurs when f double prime equals 0 and changes signs. So we need f prime to go from increasing to decreasing or decreasing to increasing so it's really also a min or max on f prime, but we'll get ahead of ourselves here. It always makes the most sense to me to go all the way to f double prime to talk about points of inflection, and that way I don't have to do the whole jumping in between f prime and f double prime and going back and forth. Anytime I see point of inflection or concavity, I go straight for f double prime because I know if that equals 0 and it changes signs that it is a point of inflection on f. Okay, so I want you to look at this little section over here. I'm going to have you pause the video for a second, and I want you to go ahead and fill in anything that you know. So, go. Something that could help with this section is anytime I am looking at f prime to think the slope of f, anytime I see f double prime, sometimes it helps to think the slope of f prime, but a lot of times it helps to think like concavity or point of inflection of f. So at the very beginning, we've got f of x is increasing. That would mean that the slope of f prime, is positive. For f of x decreasing, the opposite is true. The slope of f is negative. If f has a min or a max, that means that f prime of x equaled 0, but also had to change signs. I think we've got a more specific one down here in a minute. If f of x is concave up, so this is what we're adding in today, then that means my f double prime will end up being positive. So notice we've got concave up here for f. It was above the x-axis for f double prime. If we're concave down for f, that means f double prime will be negative. Now we're changing it up a little bit. F prime changes from positive to negative, so we're saying the slope of f changes from positive to I was looking at that one below it, changes from negative to positive, so we'll end up having a min. So we went from slope down to slope up. If f prime changes from positive to negative, we'll have a max. And both of these, I guess I should specify, these are relative. It does not have to be the absolute min or max. If f prime is increasing, then that means, so we're looking right here, my f double prime, which that would be the slope of this, so if it's increasing, then its slope is positive. If f prime is decreasing, then its slope is negative. And then our last one, if f prime has a min or a max, we're thinking about its slope, so that would mean that its slope would be 0, and it would have to change signs. This definitely takes some training your brain to be able to do all of these things, but it helps to be thinking the slope of f, the slope of f prime. So let's see what this looks like in action. You've got two examples at the bottom where we're looking for all of the points of inflection. So we've just learned that our point of inflection is where concavity changes, and that happens when f double prime equals 0 and changes signs. So anytime I see inflection or I see concavity, I'm going straight for f double prime. So I'll start with f prime. This is just using the power rule. So my 3 times 1/3, and then x squared minus 1. And then my f double prime of x will equal 2x. And the nice part about talking about points of inflection and concavity, whenever we're going for an f double prime, for polynomials at least, our function is more simple. It's easier to solve. So now I'm saying that f double prime is equaling 0. So if I'm looking for where 2x equals 0, it's just an x equals 0. And then I always want to make sure that it is changing signs there. Remember, relying back on just graphing that function is the easiest way. So f double prime being 2x is a line with a positive slope. Oh, missed 0. Fixed it. It does go from being negative to being positive. So I do have a point of inflection at x equals 0. I'm going to go ahead and add in our concavity here, that we would have a point of inflection at x equals 0. But also, I know that we're going to be concave down from negative infinity to 0, because that's where our function f double prime, it's always kind of helpful to put that out to the side so we know what we're looking at, is negative, and then we're concave up from 0 to infinity. And I'm not going to include 0 because that's my point of inflection, so that's really where it changes. Just like if I'm talking increasing or decreasing, we don't include the minimum, the minima or the maxima, because it is changing from increasing to decreasing or vice versa. So this is where it changes concavity. Okay. So why don't you go ahead and pause the video and see how far you can get with this one. Same thing, still a polynomial, you're finding points of inflection. So hopefully we got to this point where we found the second derivative and then set it equal to 0 and solved. We get a plus or minus 2. So again, going back to my f double prime, easiest way to see where it's above and below, or if it crosses, is to look at this function and see that it's a parabola, it's facing down. So I'll look something like this. My f double prime is below and then above and then below. So I do have 2 points of inflection here. -2 and 2. And then if I'm giving my concavity, I know that I am concave down. My f is concave down from negative infinity to -2, and then also from 2 to infinity. And then we're concave up on f for -2 to 2. Which I think, especially with polynomials, it helps us to go ahead and connect and see why that's happening. We will eventually do curve sketching, where we are taking all of this information and trying to come up with the closest picture that we can for f without using a calculator. So if we were to go ahead and look at f, I don't know if I can fit these both in this screen at the same time. Okay. Pretty close. So our f of x, we can actually factor, and it was 4th degree, and so we're looking for 4x intercepts. 2 of them end up happening at 0, and then we've got a negative radical 24 and a positive radical 24. So we can see, it's kind of creating an M, that it is concave down until about -2 is where it changes concavity, so that would be where our point of inflection is. And then again, now it's concave up until we get to about a +2. And that's our second point of inflection. Now it's concave down again. So whenever we are trying to come up with the most accurate picture that we can for f, that lets us know, okay, that's where I should have my tangent lines are going to go from being above to now they're below my function. On the back, we've got a graphing approach to connecting our, in this case, g prime and g double prime. This tells us that we've got the graph of g prime of x, and it's written right here, but anytime I'm looking at a graph and it's not just the original function, I'll write that really big next to it, that we are looking at g prime. This is the derivative of g, not g. But it's the derivative of g with the domain from -3 to 4, so those are endpoints there. For part A, it tells us to determine the values of x for which g has a relative min or max. So we have talked about this before. You're looking at the slope of g. So if I'm looking at the slopes of g and looking for a min or a max, I'm looking for that change. So if I have it below here, and now it changes to above. So at -2, decide for yourself here, are you going to have a min or a max? If we go from the slope being negative to the slope being positive, I will have a min. I'm just going to list them if we have other ones. For my 0 here, I go from the slope being positive, it's above, to the slope being below. So if my slope goes from positive to negative, I'll have a max at 0. And we're going to explain below, so I'm leaving a gap. And then we've got one more time that it changes. I go from negative slope to a positive slope. So we've got another min at 2. And then we do have one more 0, but remember it does have to change signs. That if I just have a positive slope and then all of a sudden the slope is 0, that's not actually a max if it doesn't go from increasing to decreasing. That just means that's where it ended. So we've got a min at -2 and 2, and remember when we're explaining that this is where there's a min, I want to be specific about the type of function, so I'm looking at g prime. So we'll say because g prime goes from negative to positive. You could also say that g prime is less than 0, then g prime is greater than 0. It's the same thing. And then we have a max at x equals 0 because g prime of x goes from positive to negative. Yeah. For part B, we're determining the values of x for which g is concave down or concave up. Okay, so remember we just learned about concavity, that you go all the way down to g double prime. So I may not know exactly what g double prime looks like. Okay, I might repeat myself here. I had to pause it because my dog was barking like a madman. So we're looking for where g is concave down or up. So that's what we've been talking about with g double prime. That tells us concavity and where we have those points of inflection. So since I have g prime, if I'm wanting to talk about g double prime, that is the slope of g prime. So if you might want to note there that g double prime is the slope of g prime. And that's what tells us concavity. So if I'm looking for my function g to be concave up, then that means I'm looking for the slope of g prime, which is g double prime, to be positive. So if my slope is positive, that means I'm concave up. If the slope is negative, I'm concave down. So our concave up areas are going to be from, looks like -3 to -1. And then we're also positive slope from 1 to 3. And then g would be concave down on -1 to 1. And then from 3 to 4. So we should hit everything here. We went from -3 to -1, -1 to 1, 1 to 3, and then 3 to 4. So everything should be included, just like if we talk about a function being increasing, decreasing, or constant, it has to fall under those categories at all intervals. For explanation, we can say that it's concave up because we could use g prime. So we could say because g prime is positive, or sorry, because g prime has a slope that is increasing, or we can say because g double prime is positive. So either is fine, since we've said that g double prime is the slope of g prime. Well, actually, even if we didn't say that, either of those explanations work. Since we're looking at g prime, let's go ahead and use that. So we'll say because g prime is increasing, And then we've got concave down because G prime is decreasing. Which if you wanted to qualify that this would be the same as G double prime is positive because it is the slope of G prime, and if G prime is increasing, the slope is positive, and that this is the same as G double prime being negative. So then in part C, we're trying to put all of this together and come up with a graph of G. So notice that it says a graph, so it's not going to be perfect, it's not the graph of G, but it should fit all of the things that we know, the mins and maxes, the concavity where it's concave up and concave down. We've got the slopes with our graph of G prime. So we're just trying to make all of those things true. They do give us these two values that we've got. G of -3 is 3. So I would start there. So that tells us my endpoint, that it starts at -3, 3, and then it's going to end at 4, 6. So that's good information. And then I think I would start with your mins and maxes, that we know there has to be a min at -2. Now we don't actually know where it is at -2. It could be that it's like right below this where it starts, but it could be way down here as well. My hint here is that if we don't know exactly where that's at, to go ahead and make it pretty low to where we can see when we're sketching it in a minute that it should be a min. So I would put it below the x-axis. Same thing for our min at 2. And they don't necessarily have to be in the same spot. One of them could be lower than the other one. Again, this is just a sketch. We don't actually know those y values at this point because we don't have a function to plug them into. Then we've got a max at 0, and same thing, I would go ahead and put it somewhere above the x-axis. Doesn't mean that that's actually where it's at, but we do know that it's higher than the other points in its area because it's a relative max. Okay, so this gives us a general sense for what we're doing, but then we can also use the fact that we are concave up from -3 to -1. So right here is where I'm changing my concavity a little bit. And so I could go ahead and decide where I want that concavity to change. That means that this whole time that I need to be concave up. So as long as I am going through to -1, I'm concave up, and this is where it's going to change. So think about those tangent lines being below the function, and now this is where they're going to be above the function, or go to be above that little point of inflection. It doesn't have to be anything crazy. I'm just going from, I was like this, and now it's going to be drawn like this. So now we've got concave down from -1 to 1, so all the way until somewhere over here. So that's where it changes. Now I'm concave up again until 3. So somewhere in my x value of 3, maybe it's right there, my concavity changes again, and now I am up at the top. So this is one version of g of x that has all of the things that we found. It's got a min at -2 and 2. It's got a max at x equals 0, the 2 points that they gave us, and then our concavity makes sense as well, which means that my slopes should make sense too, that g prime was negative from -3 to -2, so I've got negative slope, and then a positive slope where we're above for g prime. I've got a negative slope where I'm below again for g prime, and then I'm above here, so ending with a positive slope where my point of inflection changed. Oh no, starting here, sorry, 2 to 4. The last thing that we're going to look at is the second derivative test. So now that we know some things about f double prime, I can actually use the information from that to decide whether I have a min or a max. So I could rely on my g prime changing from increasing to from positive to negative, so that my g changes from increasing to decreasing, that kind of thing. But I could also use concavity to decide if I have concave down, it has to be a max. If it's concave up, then it has to be a min. So the second derivative test says that if we're on a function f of x, if f prime of c equals 0, so we're saying that the slope of f is 0, then the second derivative test would say if f double prime of C is greater than 0, then C is a relative min. So basically we're saying that the slope is 0 and the concavity is concave up. So if the slope is 0 and we're concave up, it has to be a relative min. The opposite is also true. If f double prime of C is less than 0, then C is a relative max. So again, we're saying if we've got a slope of 0 and our concavity is concave down, then it has to be a relative max. This is not a great picture, I'm sorry. You know what I'm trying to do. Our concavity is concave down, it has to be a relative max. And then sometimes if we get a situation where f double prime equals C, f double prime of C equals 0, then the test is just inconclusive. Inconclusive. Ugh. So in that case, it doesn't necessarily mean that it's not a relative min or max, it just means that we'll need to use something else. That test did not help us. Okay, so I wanted us to look at a problem that we were looking at yesterday, I believe from the homework. So I've already got I don't know if I can get this to work out. I've already got the relative extrema going on, so we've looked at f double prime equaling 0, and then already found this uses the product rule and the chain rule. So already found the derivative, and in this case we had to factor out an x plus 2 and then simplify what was left over. So you might look through that and see if you agree with it. Remind yourself of that product and chain rule and factoring. But then we found that the two relative extrema were -2 and -4/3. Normally we would go ahead and graph those and see this is facing up, and so we would see where it was positive and negative, and wherever it changed from positive to negative we would have a max, wherever it went from negative to positive is min. But by our second derivative test we can go ahead and take it one step further and find the second derivative. And our first derivative is here, so I could either multiply this out, it would just be foiling, or I could use the product rule, but I think we need practice with the product rule always. So we've got the derivative of the first, it's 3x plus 4, plus the derivative of 3x plus 4, 10x plus 2. And we could simplify this, it really doesn't matter either way. We're going to end up with a 6x, and let's see, a positive 4 and a positive 6, so positive 10. So we get a 6x plus 10. And then our last, oh sorry, I thought I was looking at the wrong thing. There was a negative, never mind. So now to use our second derivative test, we're taking that f double prime and saying, okay, I know that these are critical values. So if I'm testing f double prime of -2, and it really doesn't matter what this value is, it just matters whether it's positive or negative, that whenever I plug in -2, I get out a -2. That would mean that, and this is just a coincidence, it ends up being the same thing, but since this is greater than 0, that would mean that less than 0, that would mean that we're concave down. No, can't fit it in there. We're concave down, so that means that -2 would have to be a relative max. We'll write that in here in a minute. Same thing with our -4/3. We would go ahead and plug that into our f double prime. And let's see, we would cancel here. We got a -8, so we end up with a positive 2. So in this case, since our f double prime is positive, that means that we're concave up. So our conclusion here would be that there's a relative max at -2. And a relative min at -4/3. So this would be helpful maybe if we weren't sure exactly what the function looked like, or if we just didn't want to do like the trial and error thing where you plug in something into different parts. But also you could be given a multiple choice question where maybe they tell you x equals -2 is a critical value and f double prime of -2 is greater than 0. What's happening there? So in that case, you wouldn't have enough information to find what f double prime was f prime was doing. You would just know that f double prime was positive, and so that would mean that it was concave up, and it would have to be a min. That kind of situation where that's all the information that you have. Okay. So last question, I want you to go ahead and pause it. You are finding the critical values. So if you need an example of that, it's right above it. And then use the second derivative test to classify them as a relative min or max. So pause the video, try it yourself. I know that area is really small. If you need to use another piece of paper, use it with a piece of paper. Okay, so the first part of this, your critical values come from where f prime equals 0. So finding that first derivative, setting it equal to 0. This one did require that more challenging type of factoring, so looking for two numbers that multiply to be 21 and add to be a -10 to break up that middle term. But then once we've factored by grouping, you should get that the critical values are 1 and 7/3. And then our second derivative test would say, for f double prime, and that's where that -10 came in, 6x minus 10, I knew it was somewhere. If we try f double prime of 1, we should get -4. So since that means we are concave down, we have a relative max at x equals 1. And then for f double prime of 7/3, Jack, stop it, buddy. For f double prime of 7/3, we get a +4, which means that we're concave up. So we've got a relative min at 7/3.